My name is Leah, and I'm here to talk about one of the most challenging problems facing developers today: how to extend the battery life of mobile devices. The screen on today's smartphones, tablets, and laptops consume a tremendous amount of energy as consumers demand to have clearer, brighter, higher definition displays. Because of this, I would like to explore how programmers can take advantage of OLED screens to make energy-efficient user interfaces. During this video, I will begin with a basic introduction to OLED screens and compare them to traditional LEDs. I will then explore algorithmic techniques for developing energy-efficient GUIs and end with a look into the future of the technology. Before we can understand the advantages of OLED screens, we first have to see how they work. Shows a cross-section of a typical OLED screen. As you can see, the screens have 5 main components. The first layer is the substrate. This is the clear plastic, glass, or foil used to support the other components of the screen and protect them from damage. Next is the anode. This is a positively charged layer of electrodes that remove electrons from the system. They leave behind electron holes wherever an image needs to be darkened. Next are the organic layers. They are made up of organic polymers that have luminescent properties. The first organic layer is the conducting layer. The chemical polyaniline, or some similar conducting polymer, is used to transport electrons to the anode from the organic layer. Then we have the emissive layer, which is made up of a polymer such as polyfluorine that transports electrons from the cathode into the organic layers. The polyfluorine will emit light proportionate to the electrical charge applied to the layer. Lastly, we have the cathode, which is a negatively charged electrode that injects electrons into the organic layer as a current flows through the device. In other words, when a pixel on an OLED screen needs to be lit, an electrical current is sent to the negatively charged cathode. An electron goes from the cathode into the organic layer. Then the organic layer is illuminated before the electron is absorbed by the anode on the other side. A constant stream of electrons creates the brightest pixels. To darken them, simply reduce the rate of electricity. To get a black pixel, stop the flow of the electrons altogether. Traditional LED screens work completely differently. They use light-emitting diodes as a source of backlighting for LCD screens. In front of the LED panel, there are 3 layers of significance. The first is a polarized filter. This works by taking the light from the LED back panel and only letting through horizontally polarized light. A second filter only lets vertically polarized light to get through. This blocks any light that has already come through the first filter, creating a black screen. In between the 2 filters, you get a layer of liquid crystals. Compression from the 2 filters forces the crystal molecules to line up and twist into a vertical position. As light passes through the first filter, it reflects off of the crystals and bends until it can pass through the second filter. This causes the screen to turn a bright white. To control the amount of light passing through each pixel, an electric current is passed through the liquid crystal layer. The crystals will align themselves in the direction of the current, stopping the light from passing through once again. The strength of the current controls the amount of light coming through. For this configuration, the stronger the current, the darker the screen. But with that said, other screens are configured in the opposite direction, which switches the effect of the electric current. Despite the fact that electricity controls the brightness of the pixels, the back panel on these screens consume a significant majority of the power used overall by the system. So, assuming the brightness of the backlight is constant, which is the case for many screens, there will be very little difference in power consumption, regardless of how much light is actually passing through the filters of the screen. Going back to OLEDs, we see a very different pattern of power consumption. Since every pixel provides its own source of light, the brightness of a given pixel is more significant in determining the overall power consumption of these screens. Since the correlation is so significant, it is important for us as software developers to create user interfaces that take advantage of this feature. With that said, creating an energy-efficient GUI does not mean that you have to use exclusively dark colors. Some colors can be approximated by more energy-efficient ones that the human eye can't distinguish from the original. The first algorithm that we will look at is a technique developed by a team from Simon Fraser University. Their goal was to find an algorithm to choose the best color set for data visualization applications like color coding a map or choosing a good color set for a graph or pie chart. The algorithm works by taking a discrete color palette of M colors of equal lightness, where lightness refers to the perceived brightness of a color rather than some mathematical representation of brightness. A subset N of colors is chosen by performing the following optimization technique. First, we calculate the energy of each color using this formula. Essentially, we find the energy consumption of a given image by subdividing a frame into a set of pixel tiles. For each pixel tile, we scan through each pixel, taking the largest of either red, green, or blue, and then taking the largest value among all the pixels in the whole tile. The brightness value of each tile is added together and divided by the number of total tiles to get an average. Once we have found the brightness value of a given color, we can sort the color set by brightness in ascending order. Finally, the first N colors are picked from the top of the list. This technique works the best for designs that can handle a discrete set of colors. But what about applications that require a color set that conforms to a certain well-defined set of perceived hues? For example, if we are working on a website and add some images to our design, how can we guarantee that the colors in the images are energy efficient? A team from Italy and Williamsburg, Virginia, have developed a technique that they call GEMMA, which is short for GUI Energy Multi-Objective Optimization for Android Apps. GEMMA is a search-based optimization technique that suggests color alternatives based on 3 objectives: reducing energy consumption, increasing contrast between adjacent GUI elements, and preserving a consistency in the color choices of the design. To do this, 3 steps are taken. The first is to estimate the power consumption of the initial design. Like the previous algorithm, we consider the RGB values of a given pixel. We then take the sum of all the RGB values for every pixel in the image, as illustrated by the following equation. Next, we identify GUI elements on the screen. Specifically, we want to identify the components that cannot be altered too drastically, such as images, or components that require a lot of contrast, like text. Components are identified through a quantization process that clusters groups of similar pixels together before the components are discretized based on color. Finally, a search-based algorithm is used to find a near-optimal color set without going against the 3 objectives stated previously. Overall, this algorithm seems to be very successful at reducing power consumption. On average, the proposed solutions provide a 42% drop in the power consumption of a device simply by altering the color schemes of an app. So now that we know some algorithms for improving the performance of OLED screens, what is the future of the technology like? At this year's Consumer Electronics Show, the tech company LG introduced its newest television model, a rollable OLED display panel. While an 18-inch rollable display was introduced in 2016, this year's model is the first to be scaled up to 65 inches and the first to include a 4K resolution. At this time, the technology is very expensive to make at an estimated value of $26,000. These models may not be available to the public until at least 2020. At that time, LG is expected to complete an $8 billion facility that is in Paju, South Korea, that is designed specifically for constructing OLED screens of all sizes. Tech companies are also developing transparent OLED screens. Many believe these will have applications in retail displays and wearable devices. While the cost of building an OLED screen remains high, it will be likely that in the next few years, smaller devices like smartphones will continue to be the driver of this technology. As a result, programmers will be able to take advantage of this technology for quite some time to create environmentally ethical software. With that said, thank you for listening to my presentation. Feel free to leave a comment below.